So we are here at the University of Western Australia, and we're doing some research with colleagues here and at the University of Melbourne, and also several universities in the United States, to try and understand some better methods to protect our coastal shorelines. Right now we have a lot of coastal change happening due to climate effects, storms that are coming in, sea level rise, those sorts of things. And we need to protect the infrastructure that's there as well as the habitats that are located there. And so there's a strong desire globally actually to try and protect these areas for future.
We're looking at nature-based methods for coastal protection, and we're specifically focusing on oyster reefs. So there's three different components of the team. There's the reef design team, which is mainly us in Australia. There is an oyster recruitment team, and really looking at how oysters settle on these structures and grow and survive and become self-sustaining, because that's the point of a nature-based structure. And then we have a third team that's looking at genetics of oysters and how we may be more adaptable to future conditions and disease and things like that.
So the reason the modules look like this is because we're trying to achieve two things with the reef. The first is to attenuate enough wave energy to actively protect the coastline, as well as to create an environment that is suitable for oyster recruitment and oyster growth. So we designed a reef module that ultimately had a lot of porosity to trap the water coming in and take a lot of energy out of the waves, so there was minimal erosion and flooding behind the reef on the coastline. We also create a reef that has a large variation in height so that the oysters have a huge range of environments in which they can potentially settle and grow.
So basically, to create the modules, we've used a lot of information on the ecological side as well as from the wave attenuation side. And we've come up with a really nice interlocking design that essentially optimizes wave attenuation. It's really balancing having the units be as complex as possible, because obviously the more complex that they are, the better they are for ecological value. But we have to balance that with making them really economical to produce on a large scale as well.
So UWA is doing a lot of testing of these reef modules in the wave flume. And the idea is we have to attenuate 90% of the wave energy for this project to proceed. So we are designing a reef that has enough variation and creates enough drag to take 90% out of the energy out of every wave that the reef encounters. It is difficult. If it were that simple, there'd be a lot of these types of solutions. And so what we've done is we've designed something with a lot of complexity. The complexity of the geometry of the reef actually allows for a lot of energy to be taken out of the wave by either creating braking or creating drag on the obstacles. And both of those things take energy out of the wave and dissipate it and protect the coastline behind it. So it's really the bespoke porosity of these modules is really one of the secrets to their effectiveness. They allow the water to enter, but not leave immediately, and so all that energy gets dissipated.
So we're really still at the early phases of this research, but we have really promising results. So we're showing that this structure that has been designed by the group that's involved in this project has been very effective at attenuating wave energy. So the next step is really integrating that with the biologists and understanding how oysters can grow and thrive on this reef structure and deploying this in the field as a large-scale reef.